Okay, hey, my chemistry students. We're going to get into what I think is some pretty awesome stuff. Some stuff that's going to really start cracking the code of our thermodynamic universe. So we're going to get into these two quantities called the Gibbs and Helmholtz free energies and the respective criteria for spontaneity. Okay. So let's first talk about this business of criteria for spontaneity and building up all of the things that we need. So recall we've discussed the Clausius inequality, and we'll just restate that ds is greater than or equal to dq over t. And of course I can rearrange this, as we'll see, will be more useful for us in the coming discussion. So if I subtract that over from either side, we can see ds minus the quantity dq over t must be positive. Okay. So now let's play with these two things that we've talked a lot about: heating at constant volume and heating at constant pressure. So if you recall, when we're dealing with heating at constant volume, du, our change in internal energy, will just equal dq. And I'll put that little v right there so that we remember volume is being held constant. Okay, well, with that, we can plug that into the Clausius inequality given above. So that will go as ds minus du over t must be greater than or equal to 0. So I just replaced dq here with du. And so now if we do a little bit of algebra on this expression here, so I'll write that now as t ds must be greater than or equal to du. So I added that over to that side and multiplied both sides by t. This starts to give us a criteria for spontaneity. Okay, so for example, if we think about what has to happen to ds in the process, in a spontaneous process, okay, and we've been talking about constant volume here. Well, now if we impose that internal energy is constant, we can see that ds must be greater than or equal to 0 at constant volume and constant internal energy. This, lo and behold, boys and girls, is our first criteria for spontaneity. Okay. So now similarly, what about du? Okay, well, once again, we're still in this constant volume region. But now what if we impose that entropy is constant? Okay, so then that would indicate that du must be less than or equal to 0 at constant volume and constant entropy. Okay, so we've come up with another criteria for spontaneity. Awesome. So let's write that down. Criteria for spontaneity. So in other words, entropy must increase at constant volume and constant internal energy for a process to be spontaneous, and internal energy must decrease at constant volume and constant entropy for a process to be spontaneous. I'm going to rewrite that just a little bit to make that look slightly nicer, although only just a little bit, right? Okay, so now what about heating at constant pressure? Well, similarly, that deals with the enthalpy, which equals dqp, right? So heat delivered at constant pressure is equal to the enthalpy. And again, we can plug that into our Clausius inequality and say ds minus dh over t must be greater than or equal to 0. And then doing a similar algebraic rearrangement, we can say t ds must be greater than or equal to dh. And now we can play this exact same game. So we recognize ds at constant pressure. And now in this case, if we hold enthalpy constant, we can see that quantity must be positive for a spontaneous process. Okay, so let's box that off. And then now if we look at changes in enthalpy at constant pressure, now we'll do the same thing. We'll hold entropy constant, and we can see that that quantity must be negative for a spontaneous process. So just like that, we've developed 4 criteria for spontaneity. Okay. So let's keep going with this. So I'm going to introduce 2 new thermodynamic potentials. You've probably talked a lot about Gibbs. I know we talk about Gibbs in general chemistry. But you probably haven't heard of the Helmholtz free energy. So by definition, the Helmholtz free energy is the following. 3 equal signs means it's a hard definition. So U minus the quantity Ts equals the Helmholtz free energy. Or for infinitesimally small changes, dA is equal to du minus T ds. Right? Well, noting here that ds equals Q over T, we recognize the quantity TdS equals Q. We also can't forget the first law, du equals Q plus W. And so now we can see here du minus Q must equal W, which is exactly what we have here. So in other words, the Helmholtz free energy by definition is work. It is the work we are free to use to ensure a process must be spontaneous. So Helmholtz free energy is work. Okay. And if we start playing around with these same relations now, we remember from our Clausius inequality, TdS must be greater than or equal to du. So now looking at these quantities here, if TdS must be greater than du for a spontaneous process, then that means this quantity, dA, must be negative for a spontaneous process. Okay? So we can say dA, and now here, because we're dealing with internal energy, we know that's a constant volume situation. And now here we've got temperature in the mix. So let's hold temperature constant, and we can see that that quantity must be negative for a spontaneous process. Okay? Well, what about equilibrium? Well, as it turns out, if dA at constant V and constant T equals 0, then we are at equilibrium. Okay? So, and I'll give that a little clouded box right there. Okay. So now, what about the Gibbs free energy? Well, by definition, Gibbs, 1, 2, 3, is H. Let's see, I almost wrote plus, but it's not plus, it's minus. H minus Ts. And now, similarly, as we might imagine, this quantity also equals work for the same arguments that we just discussed. Okay, so the Gibbs free energy is also work. It is the maximum work we are free to use to ensure a process is spontaneous. Okay? So now we'll play the same game that we did before. We can say dg equals dH minus T ds. Once again, T ds must be greater than or equal to dH for a spontaneous process. So we can see if this quantity TdS must be greater than the quantity dH in a spontaneous process, then dg must be negative for a process to be spontaneous. So now similarly, we can say dg, and because we're dealing with enthalpy, that's a constant pressure situation, we'll impose constant temperature, because that's the last variable we have there to fix. And now we can see that will be negative in the due course of a spontaneous process. And just like we said with the Helmholtz free energy, dg at constant pressure and temperature equals 0 also corresponds to equilibrium. So summarizing all of our criteria for spontaneity, they're all right here. So I know this looks like a lot, especially keeping track of all of these T's and P's and S's and P's and so on. So as we get to the end of this module, we're going to go through a really handy mnemonic, a cheat code, if you will, on how we can remember all of these things and keep them straight. But for now, we'll recognize here are our spontaneous criteria. So if any of these conditions are true, then that means our process must be spontaneous. If any of these conditions are not true, our process cannot be spontaneous. We're going to keep going down this rabbit hole in the coming videos. I'll see you then.